Section 4.2 is going to introduce Rolle's theorem and then a more general version of Rolle's theorem called the mean value theorem. The mean value theorem is going to be the basis for a lot of what we do in Chapter 4 in terms of increasing and decreasing functions. But let's start with Rolle's theorem. Rolle's theorem has a very simple premise to start with. It says that you have a continuous differentiable function and the endpoints of the function, that is f of a right here and f of b, are the same. That is, they have the same heights. So f of b equals f of a. If that's true and you have a continuous differentiable function, then what's happening? Then your function is going to increase and then it has to come back down, decrease, and get back to where it started from. Or it decreases and then has to eventually get back to where it increases. Now, at that point where it turns around, where the function stops increasing and starts decreasing, there's kind of a brief pause. What special magic thing is going to happen when it pauses and kind of changes its direction from increasing to decreasing? Yeah, you're going to have a horizontal tangent. And that's what Rolle's theorem guarantees, is that at some point there's going to be some value of c such that f prime at c equals 0. There's going to be a horizontal tangent somewhere in there. Now, the actual formal definition of Rolle's theorem is on page 210 of your book. Let's take a look at that real quickly. So here it is. F is a continuous function on the closed interval, and it's differentiable on a to b. That's called the open interval. Then, if the value of the function is equal at the endpoints, there's at least one place where you have a horizontal tangent line. At least one. Okay, so let's look at a couple early examples. And to that end, you've got a nice handout that's going to speed us up a little bit. So let's take a look at problem number 2 here. Now, I debated if I wanted to include this on the handout or not. Problem number 2 asks us to consider the graph of y equals the cotangent of x over 2 on the interval pi to 3 pi. Now, certainly one of the requirements of Rolle's theorem was that at the endpoints of your interval, the function had the same value. Well, here's pi and here's 3 pi. At the endpoints of the interval, great. Cotangent of pi over 2 equals 0. Cotangent of 3 pi over 2 equals 0. So plugging in these points gives me exactly what I need. But can I apply Rolle's theorem, though? Do I have enough that I can apply Rolle's theorem? No. There's something that's missing. There's actually a couple things. Good, it's not continuous. And of course, if it's not continuous, what else is missing? It's not differentiable. It's neither of those. So we can't apply Rolle's theorem because we don't have a continuous differentiable function on that interval. So, nice. Rolle's theorem doesn't apply. Let's slide over and look at problem number 4. The function in this case is f of x equals the square root of 2 minus x raised to the 2/3 power and then cubed. Now, Desmos is not clever enough to figure out these values. Does anyone recognize, say, 2.828, etc.? What's that approximation of? Very good. So that's 2 root 2, and that's negative 2 root 2. That's the actual edges of the domain there. But as before, what you can see here is on the interval negative 2 root 2. Basically, it turns out to be negative square root of 8. So let me just cheat. Negative square root of 8 to square root of 8. On that interval, or even on, no, actually I think that, no, the book uses -1 to 1. But either interval is fine. Well, the function is continuous here. Does Rolle's theorem apply? Why not? Nice. It's not differentiable at x equals 0. So right here you have what we called on the first test a corner point. The derivative doesn't exist at x equals 0. So Rolle's theorem does not apply. Because f of x is not differentiable on any of these intervals, say -1 to 1. Okay, so just a reminder that in order to apply these types of theorems, you have to make sure that their assumptions are met. Okay, well let's work with one where the assumptions are clearly met. And that would be problem number 12. So problem number 12, f of x is x minus 4 times x plus 2 squared. And we're going to look at this on the interval -2 to 4. Now the nice thing about problem number 12 is that we're working with a polynomial. Polynomials are, first of all, continuous, and secondly, differentiable everywhere. So we're not going to have any problems with this not meeting the assumptions of Rolle's theorem, other than we need to check it at the endpoints. But even that's pretty easy. Let's take a look at f of -2. Now I'm not going to take out my calculator for this. What do you notice about this second term when you put in a -2? 0. Squared is still 0 times whatever is still going to be 0. So f of -2 is 0. What about f of 4? Well, 4 times 4 is 0 times whatever. It's still going to be 0. So the endpoints have the same y coordinate. Now in this case it's 0. And some books actually write that, Rolle's theorem says that the endpoints have to be 0. Really, a little bit more loosely, the endpoints just have to be equal for Rolle's theorem to apply. But let's apply Rolle's theorem. Let's see if we can't find the place where the derivative is equal to 0. It's guaranteed to be there. So let me go back here. F of x is x minus 4 times x plus 2 squared. What rule do I have to use in differentiating this? Yeah, product rule and chain rule. So one kind of heads up here, I would probably suggest we avoid squaring it out and multiplying it all out. It's going to be easier for us in terms of factoring and setting it equal to 0 if we just use the product rule and then try and clean it up from there. So it's going to be, well, let's call this u and v. It's going to be u prime v plus v prime u. What's u prime? 1 times x plus 2 squared plus v prime. The v prime, technically you have to use the chain rule here, right? It's the derivative of the outside, 2 times x plus 2 to the first power, times the derivative of the inside. But what's the derivative of the inside? Good, it's 1. Times the other function, x minus 4 times u. As far as cleaning this up is concerned, I don't recommend squaring this, distributing, and then adding like terms. Is there something else I can do to clean this up? there's a GCF of an x plus 2. So let's factor out that greatest common factor. X plus 2. And that leaves behind x plus 2 plus 2 times what? X minus 4. And see, now all I have to do is combine a couple linear terms here. That's going to be x plus 2 times, let's say I'll have x plus 2x, that'll be 3x. And then 2 minus 8 will be a minus 6. Last but not least, I mean, I don't really need to go this far. I think right here you can probably see where the zeros are, right? Where would the zeros be? Negative 2 and 2. You can, if you want, factor this out a little bit more. You can factor out a 3 from here. 3 times x plus 2 times x minus 2. Yay. So you can now see where this is equal to 0. It's at x equal negative 2 and x equals positive 2. So there's your solution. Those are the 2 points that are guaranteed by Rolle's theorem. Places where the derivative is 0. So other than an application of Rolle's theorem, what I wanted you to see was this little trick with the factorization. And instead of multiplying things out, we pulled out the GCF there and then completed things. So any other thought on problem number 12 here? Let's take a quick look at the graph and see if the graph confirms what we were suspecting about it. Y equals x minus 4 times x plus 2 squared. And let's change the viewing window a little bit. Going to need to go a little bit deeper on the y-axis. So let's go down to negative 40. There we go. So at x equal 2, the function has a minimum. And at x equal negative 2, the function has a maximum. But both of these places are places where you have a horizontal tangent. That's exactly what Rolle's theorem was telling us, is places where you have a horizontal tangent. Let's move on to problem number 20 since there's no other thoughts on problem number 12. This time we're going to look at the secant function. So f of x is secant of x on pi to 2 pi. Pi to 2 pi. So the instructions say, in the exercise, determine whether Rolle's theorem can be applied on the closed interval a to b. If Rolle's theorem can be applied, find all values that satisfy Rolle's theorem. So can we apply Rolle's theorem here? I don't think so. I think there's a few things going wrong with this one. First of all, let's think about f of pi. F of pi is going to be the secant of pi, which is 1 over the cosine of pi. What's the cosine of pi? Negative 1. If I looked at f of 2 pi, I'll get 1 over the cosine of 2 pi. So right away, we're running into problems. I think you'd run into further problems with this if you took a look at the graph. So let's shut this off real quick and take a look at y equals secant of x. and we're looking at the interval from, say, pi to 2 pi. Yeah, so you got a vertical asymptote here. The function's not continuous. So I'm trying to see, let's take a look at a couple curves here real quick. If we do y equals 1 and y equals -1, might help us determine a couple points. So there's pi, and over here should be 2 pi. So the problem that we're running into is that there's a vertical asymptote here. Not only is the function not equal between these 2 points, but it's not continuous and not differentiable. So there's a whole host of things going wrong with trying to apply Rolle's theorem to the secant in that interval. Well, let's back up a step then. Let's take a look at the cosine of 2x on the interval -pi to pi. So y equals cosine of 2x on the interval. In fact, you can do this. Let's do negative, where is it? -pi to pi. Oops. Wrong notation. Less than x less than pi. That's a little bit better. So all we have to do is worry about the function on this interval. Does this satisfy Rolle's theorem? Yeah, absolutely. So at the endpoints here, at pi and a -pi, the function has a value of 1. So we're good there. Let's work on the rest of it. It's continuous and differentiable in that interval. 18, so f of x is cosine of 2x on the interval -pi to pi. F of x is continuous and differentiable on -pi to pi. So that part's good. And the other part that we needed to check was this. F of -pi equals f of pi. And both of those gave us a 1. So all the assumptions of Rolle's theorem are met. Now it's time to try and find the points that actually solve Rolle's theorem. So this is where you get to do a little bit of work. You need to find f prime of x and set it equals 0. So basically you're going to solve and find those points. Find where the derivative here is equal to 0. solving it is going to be more.
I already took the derivative, and that is the derivative.
Oh, I see what you're saying.
And then I was just doing it so when I set it equal to 0.
Oh, okay. Yeah, that's actually not a bad idea.
Yeah.
Okay, I see what you're doing. I thought that was. I thought.
Yeah, I was differentiating this part.
Okay.
I'm a little confused on what to do here.
Okay. Let me give you a hint / reminder. And it might. There's a couple ways to solve this. So, but one hint is that the sine of 2x is 2 times the sine of x times the cosine of x. So you might be able to use that in terms of solving for where the derivative is equal to 0. Actually, probably make it a lot easier than other ways that I can envision. Not alone though in desiring to use the product rule there. I'll make mention of that. So the first thing we need to do is to find the derivative here. Now when you differentiate this, one thing I want to be clear about, you're not going to ever use a product rule. It's not the product of cos times 2x. You can never do that. We can smile about it now, but I guarantee that somebody on the test is going to want to use a product rule here. It happens. I understand the overwhelming desire to do that, but fight it. Now, as far as the derivative here, you have to use a chain rule. So it's the derivative of the outside. What's the derivative of cosine? Minus sine of 2x times the derivative of the inside. The derivative of the inside is 2. So basically minus 2 sine of 2x. Well, before we do that, I'm going to use this trig identity over here. That sine of 2x is 2 sine of x cosine of x. So minus 2 times 2 sine of x cosine of x. Or better yet, minus 4 sine of x cosine of x. And the nice thing is that it splits this up into a product of a couple things that I'm pretty familiar with. I want to know where f prime of x equals 0. So let's set f prime of x equal to 0. That's going to mean minus 4 sine of x cosine of x equals 0. If you're bothered by that negative 4 or just don't want to deal with it, then one thing you can do is divide both sides by negative 4. Doesn't hurt, and it gets rid of the negative 4. You're left with sine of x times cosine of x equals 0. And that's great, because what you've done is you split up your problem into two smaller problems. We've got something times something equals 0. One of those somethings, either sine x or cosine x, has to be 0. So where does sine of x equal 0? Where does cosine of x equal 0? Well, these are problems that we can handle. Sine is which coordinate on your unit circle? The y coordinate. So where is it 0? Where's the y coordinate 0 on your unit circle? Yeah, 0 pi and negative pi would be the easy ones, right? 0 pi and negative pi. Cosine's the x coordinate. Where is it going to equal 0? Negative pi over 2, pi over 2. And 3 pi over 2 is outside our interval. Remember, we wanted solutions on the interval negative pi to pi. So we're not going to have to go farther than this. Let's see if we can't confirm these results. Let's go back to our graph, Desmos. Let's do a couple clicks here. Well, we had a zero derivative here. We got that one. Negative pi over 2, pi over 2. And there's pi. And here's negative pi. So we're in good shape. We got all 5 of the places where the derivative is 0. Any other questions or thoughts on problem 18 there? Are we doing pretty good with Rolle's theorem? Comfortable there, I hope? What we're going to do is we're going to expand on Rolle's theorem. Rolle's theorem is a little bit restrictive in as much as it assumes that the value of the function is same at both of these endpoints. All right, that's a little bit restrictive. I mean, if you have it, great. If not, you should still be able to do something. To that end, let's introduce the mean value theorem. Now, the mean value theorem, they're using the word mean as a synonym with average, not mean as in being really caustic or, taking pot shots at somebody in a debate, for instance. They're meaning mean as in average. So what's the average value theorem say? Would be another way to put it. And here's a nice graph that kind of depicts what the mean value theorem says. You're going to start out with the same kind of assumptions that you have in the Rolle's theorem, in as much as you have a continuous function and it's differentiable on the interval a to b. We don't necessarily need to assume anymore that f of a equals f of b. In fact, it's more general if we don't assume that. What the mean value theorem says is that the slope of the line between these 2 points, the so-called secant line, there's a point between a and b so that the slope of the tangent line matches the slope of the secant line. That is, f prime of c equals this slope. That's what the mean value theorem is saying. At some point, the instantaneous value equals the average value. Now the actual formal statement of that, it's here on page 212. Let me take a quick look at that. Here it is. There we go. So again, you've got a continuous function on a closed interval, differentiable on the open interval. But basically it's saying the instantaneous rate of change at some point equals the average rate of change. So it's interesting. We're going to get more out of this in coming sections when we start talking about where functions are increasing and decreasing, etc. For now, let's just practice with it a little bit. And we'll start with a nice friendly problem. No, should we start with a friendly problem or should we start with the harder one and I'll let you do the... Hang on, let me think for a second. Yeah, let's start with a friendly problem. Problem number 38. All right, so let's go back to the handout. Problem 38 gives you a function. And let's go back to there. F of x is x squared minus x minus 12. So that's this parabola. F of x is x squared minus x minus 12. Nice. We're going to look at this function on the interval from -2 to 4. So we're going to look at a couple points. We're going to look at points at x equal -2 here up to x equal 4 here. Those are the endpoints of our interval. -2 to 4. Now the mean value theorem says that the average rate of change here of this function, the function does go down and then comes back up. On average, that rate of change should equal the rate of change at some point for the function. Let's do some calculations here. X and y. At -2, the function has a value of -6. At 4, the function has a value of 0. So how is it changing on average? So that's going to be the slope of a line between these 2 points, right? Between -2 and -6 and 4 and 0. So 0 minus -6 over 4 minus -2. So I'm getting a slope of 1. The mean value theorem guarantees me that somewhere in the interval of -2 to 4, the function has a derivative equal to 1. In other words, the slope of the tangent line there equals 1. So let's find that point. What's going to measure the slope of the tangent line? How am I going to find that? Derivative. So let's find the derivative. Derivative here, f prime of x. That's not too challenging. It's a nice polynomial. 2x minus 1. I want to know where these two things are equal. Where does the slope of the tangent line equal the average rate of change of the function? So you're going to set these two equal to each other. 2x minus 1 equals 1. And I'll wait while you get out your calculators and solve. All right, I'm kidding on that one. I hope you got that one already. Just wanted to see who was with me and who was awake. So 2x equals 2, x equals 1. So at x equals 1, the slope of the tangent line matches the slope of the secant line. And you can see that. These two are nice and parallel. So that's the mean value theorem. How are we looking on problem 38 there? Is that all right? Do you have a good sense of what the mean value theorem is telling you? Let's try another one a little bit more challenging. In fact, a lot more challenging if you're trying to spend time working with this on the graph. You know what? It's actually a Rolle's theorem problem. That's okay. Now maybe we should do another mean value theorem, and then we'll go back and do the Rolle's theorem one. Let's stick on the handout then. We'll do problem number 46. F of x is the square root of 2 minus x. We're going to work on this on the interval from -7 to 0. No, let's see, -7? No, -7 to 2. I'm sorry. Let's do the same thing that we did before. We start out, make ourselves a little t-table. Look at the endpoints, -7 and 2. We're doing that for our function f of x. Let me try and highlight f of x here for us. That's the skinny kind of half of a parabola here in green. Then in yellow, what I have is the slope of the secant line. We're going to need to figure that out. And at some point, the slope of the tangent line is going to equal the slope of the secant line. So that would be the slope of the tangent line would be right here. So for the right point, those two things match. See if you can't finish this one up and finish the mean value theorem for this particular problem. Okay. I'm not seeing a lot of confidence as you pursue this problem, so let's kind of work on a few things together. 2 minus negative 7 is 9. Square root of 9 is 3. And of course 2 minus 2 is 0. Square root of 0 is 0. So the first thing you're going to need to do is calculate the slope of the secant line. So that's this line here, the yellow line. What's its slope? So m sub secant equals, well, let's find out. That's going to be 0 minus 3 over 2 minus negative 7. Now, is it surprising that you're going to get a negative result? No. As you move from left to right, this line is decreasing, so you expect a negative slope. So that's the slope of the secant line. We need to find the place where the slope of the tangent line equals the slope of the secant line. What measures the slope of the tangent line? One more time. Derivative. Good. So 2 minus x to the 1/2 power. So in order to find where the slope of the tangent line equals the slope of the secant line, I first have to calculate the derivative. What's the derivative of 2 minus x to the 1/2? I keep on wanting to put an x there. 1/2, 2 minus x to the negative 1/2. That's the derivative of the outside. Hopefully it didn't stop there though, right? Times the derivative of the inside, which is a minus 1. In other words, minus 1 over 2 times 2 minus x to the 1/2 power. So to solve here, to solve in this problem and figure out what's what and where it works, we need to decide where the slope of the tangent line, m sub tangent, which is your f prime, equals m sub secant. Those two things are what we have to set equal to each other. All right, I think I'm going to go to a different sheet of paper here to solve. So negative 1/3 equals negative 1 over 2 times 2 minus x to the 1/2 power. This is a nice proportion. We can cross multiply. So when I do that, I end up with negative 2 times 2 minus x to the 1/2 equals negative 3 times, well, just negative 3, right? Just negative 3 is good enough. If I divide both sides by negative 2, I get 2 minus x to the 1/2 power equals 3 over 2. This is a square root. Now, here's a good trick for you. You know, a lot of you could think of this as, oh, gee, that's a square root. I'll square both sides. But a nice thing to think of more generally, when you're trying to solve these types of equations that involve exponents, a quick way to solve this is to raise both sides to the reciprocal power of this exponent. What's the reciprocal of 1/2? It's 2. This idea of raise both sides to the reciprocal power works nice even if you have ugly fractions like 7/3 or 9/11, etc. You can still raise both sides to reciprocal power and be done in one step. Now on the right hand side, it's not squared anymore. I get 9/4. Let's finish solving for x. I'll subtract 2 from both sides. Negative x equals 9/4 minus 2, which I'll conveniently write as 8 over 4. So negative x equals 1/4. That means x equals negative 1/4. That's the point at which the tangent line has the same slope as the secant line, and that's already drawn on your graph right here. Right there. So at that point, the slope of the tangent line equals the slope of the secant line. Let me remind you of something you can do on your calculators to kind of check things if you want. Let's graph this function from negative 7 to 2. So the first thing I'll do is I'll put in that function into my calculator. So the window let's see, put in the function, square root of 2 minus x. And then I'm going to adjust the window to kind of match that. So let's hit the window key and go -7 to 2. Now you can hit zoom fit, that is zoom 0. Looking at the graph, I already know that, y min of 0, y max of 4 should do pretty good. You can actually go up to 3 for y max. Now what I want to confirm is the slope of the tangent line at x equal -1/4. Do you remember how my calculator can give me the value of the derivative at a point? If you hit the second key, then the trace key, that takes you to the calculate menu. There's an option here that looks promising. Yeah, dy by dx. Let's choose 6. It's going to ask you, well, where do you want your derivative? Just type in -0.25. Now, as soon as you touch a key, it's going to open up this line down on the bottom. When you press enter, it should give you the value of the derivative and the coordinates of the point. So there's the coordinates of the point, -1/4, 1.5. But the value of the derivative, what's that look like? -1/3. Nice. There's nothing wrong with verifying that you got the right answer before you hand in an exam. All right, we said and did a lot on problem 46 here. Is there anything else you'd like me to add, or maybe a detail or two that you'd like me to clear up? Let's do a couple more here. Move on to problem number 50. So problem 50, f of x is x plus 3 times the natural log of x plus 3. And we're going to look at this on the interval from -2 to -1. What should we do first? I didn't give you a nice graph on a handout this time. So what should we do first? Now let's graph it, okay? Graphing it will help us check the assumptions. What 2 assumptions are we going to look for? Good. Differentiable and continuous. Parentheses x plus 3, right parentheses, ln of x plus 3. Hit the window key. Let's type in -2 to -1 and let our calculator do the work, because I have no idea where this is going to be graphed or where it needs to be graphed. So hit zoom and then 0. Let's let our calculator do the work for us. Earn your pay. Okay. Doesn't look dramatic. Kind of looks like maybe part of a parabola, but there it is. Continuous and differentiable. What will we see if it's not differentiable? What kind of things could we see? Corner point, vertical tangent, discontinuous, a hole. Yeah. So, again, discontinuous. But we see none of that. So, we're okay in terms of it's differentiable and it's continuous. Differentiable and continuous. Good. Got that down. What should I do now? Let's find the slope. All right, so x and y. So negative 2 and negative 1. And hey, guess what? We can almost kind of cheat. I wouldn't call it cheating though. Hit the second key, then the table key. And let's type in negative 2 and negative 1. And at least get a couple values. Well, at least at negative 2, we see pretty quickly we get 0. So that's helpful. And at negative 1, we're going to get 2 log of 2. Now the decimal value for that is 1.3863, etc. If you need more digits than this holds, then take your cursor and put it on that, and at the bottom you'll see all the digits you could possibly desire. So 1.386. I need to find the slope of the secant line here. So m sub secant equals 1.386 minus 0 over negative 1 minus negative 2. Basically, that's going to be a positive 1, and the numerator is just going to be 1.386. I'm going to write 2 log 2 for the moment. So that's what it is. So that's the first part. Now you might make mistakes on these types of problems, but at least I want to see you doing two things. I want to see you calculating the slope of the secant line. I want you to find the derivative. Now if you struggle setting them equal to each other and solving, okay, at least you get partial credit for knowing what you're supposed to do. Let's find m tangent. M tan is going to be f prime of x. What rule do I have to use for f prime of x? Product rule. So, once again with the product rule, you've got a u and a v. So I'm going to want u prime v plus v prime u. See if you can't beat me in that calculation. I promise to take my time. Still taking my time. I'll start in a minute. Better hurry. I think the second term is going to be 1 when you differentiate it. Yeah. So it's going to be 1 times ln of x plus 3 plus x plus 3 times 1 over x plus 3 times 1, right? Drew to the outside times drew to the inside, but that disappears. Basically, it's just ln of x plus 3 plus 1. Yay. Now, I don't think this is going to solve to anything really, really nice. That's okay. The important thing is that you're with me up to here. We've wanted to find these two things in terms of slope of the secant line and slope of the tangent line. Solving it, okay, that can be tricky, and if you struggle with that, I can be understanding. But at least get this far. Try and get yourself as much partial credit as possible. As far as solving is concerned, I want to know where this equals this. Ln of x plus 3 plus 1 equals 2 ln of 2. Slope of the secant line equals the slope of the tangent line. I'll subtract 1 from both sides. Ln of x plus 3 equals 2 ln of 2 minus 1. I think what I'll do here, just for convenience, is get a decimal value here. Basically, you're going to raise both sides to the power e, is what's coming. But I think you might be a little more comfortable if I wrote it as a decimal value here. So the decimal values of 1.386, etc., minus 1 is just going to be 0.386, etc. it's helpful to remember the base of the logarithm. ln has what as its base? E. So to rewrite this relationship, it's going to look like this. E to this power equals this. So e to the 0.386 equals x plus 3. Last but not least, I'll subtract 3 from both sides. E to the 0.386, etc. minus 3 equals x. And that should be the point where the slope of the tangent line matches the slope of the secant line. Okay. Let me go back first to this part right here. Are you okay with what we set up in terms of m sub secant equals m sub tangent? That part's good? Solving it. Once we set them equal to each other and solving it. You okay there? You might want to look back at your properties of logarithms. One thing that's helpful to keep in mind is log base a of x equals y. Always can be written as a to the y power equals x. So that's how you're kind of unraveling these logarithm properties here at the end. So stuff like this is useful. Sometimes at the top of a test, if there's something you're worried that you're going to forget, as soon as you get your test, write it down. It's called a memory dump. That way, when I say, oh, 10 minutes left, you don't panic and go, oh, what was that identity? What was that equation, etc. You've got it written down. So important things like that, not just on this test, but on any test, write them down. It's good things to remember. Let's back up and take a look at problem number 26. F of x is x over 2 minus sine of pi x over 6. We're going to look at this on the interval from -1 to 0. X over 2 is a continuous function. Sine is a continuous function. So I'm not going to have any problems with differentiability or continuity. Both of these are continuous functions. If you subtract them, you're still going to have a nice continuous function. So am I breezing through that a little bit? Yes. But you can graph it and you'll see the same thing. Let's check out a couple things here. First of all, f of 0. If I put in a 0 here, I get 0 over 2, that's 0. Minus sine of 0. What's the sine of 0? Sine of 0 is 0. What gives you 1 when you take an evaluator of 0? Which trig function? Cosine. Yeah. F of 0 is 0. And interestingly enough, f of -1. If I put in -1, I'll get -1/2 minus sine of negative pi over 6 is -1/2. That double negative becomes a positive, and I get 0 again. So Rolle's theorem is satisfied. The endpoints are equal. What's Rolle's theorem say then? If you've got a continuous differentiable function The value of the function at the endpoints is equal. What has to happen in between? Yeah, there's a place where the derivative equals 0. There's a place where there's a horizontal tangent. How are we going to find where there's a horizontal tangent? Perfect. Thank you. Find the derivative and set it equal to 0. In terms of finding the derivative, you might find it more comfortable to differentiate this as 1/2 x and sine of pi over 6 times x. So kind of taking the x out of the numerator and writing it next to your fraction. So that way you can just see, oh, well, that's a constant. It's a 1/2. I'll just differentiate the x, or a constant of pi over 6. See if you can't find the derivative. Then I'll help you solving it. Solving it is not terribly easy. What'd you get for the derivative? So that's the derivative of the outside times the derivative of the inside, which is pi over 6. Okay, nice. We want to solve this equal to 0. Are we okay with the derivative there? I started writing your test yesterday. There's a ton of derivatives. Just so over the weekend, when you go to bed at night, sleep with a derivative formula sheet underneath your head. They'll all seep in, okay? You got to know these things backwards and forwards. All right. Yeah, I know. I wish it would work. So, all right, we're going to set this equal to 0. I'm going to pick this whole term up and move it to the right-hand side. That way I get rid of the negative sign. That's going to be 1/2 equals pi over 6 cosine of pi over 6x. So all I did is I moved this whole term to the right-hand side. I also moved the coefficient out in front, or the constant out in front. I need to solve for x. I guess what I would do first is multiply both sides by, not by 2. Yeah, let's go 6 over pi on both sides, right? 6 over pi, 6 over pi. That way I get rid of this term over here, which is nice. Get rid of that. And I'm left with really 3 over pi equals cosine of pi over 6 times x. No. Good question. I moved that term to the other side, and when it switched sides, it became positive. But thank you. It is positive. Ooh. Now what? Well done. To solve here, you're going to take the cosine inverse of both sides. 3 over pi equals the cosine inverse of the cosine of pi over 6 times x. These two things cancel each other out. That's nice. That's really nice. So I'm left with the cosine inverse of 3 over pi equals pi over 6 times x. Almost done here. Cosine inverse of 3 over pi equals pi over 6 times x. I need to finish solving for x. What's my trick to solve for x here? Yeah, multiply by the reciprocal. So multiply by 6 over pi. And not a real friendly number that we're going to get out of this. 6 over pi times a cosine inverse of 3 over pi equals x. Wow. Let's try and calculate that thing. I mean, what is that? By the way, what mode does your calculator need to be in when you calculate this? Radians. All right, so this is in degrees, so hit the mode key, go down to radians. I'll just do it this way. Hit the alpha key, type in a fraction. 6 divided by pi. Exit that fraction. And then I want the cosine inverse, so second, and then cosine of, again, another fraction. 3 divided by pi. I guess I didn't really need that part there, but I'm getting 0.57. There's also going to be a negative symmetric point on the opposite side of the origin at negative 0.57, etc. Let's take a look at our graph and see what we can come up with. So we got a solution at 0.57, etc. There's also a solution at negative 0.57. Our graph really is kind of uninspiring. When you graph this, here's what you get. Does it look like there's a maximum at negative 0.57 something? No. You've got to zoom in amazingly close. So on the y-axis, let me go down to negative 0.001 to, let's see, over here to 0.001. No, I think I got too many zeros. One. There we go. Yeah. There. That looks better. But look at how much I'm zoomed in. That's 1/100th in terms of height on the y-axis. So it's barely getting above the y-axis. But let's see about our point. Where's that point? Negative 0.576. That's pretty close to what we got on our calculator, isn't it? That's real close. And you can see it's twin on the other side of 0 right down here. But there's the point that was guaranteed by Rolle's theorem. Rolle's theorem said that there's a place where the derivative was 0, and we found it. But boy, when I prepared this lecture, it took me a little while to figure out what I had to do to be able to see that, because I'm just not used to zooming in that close on the y-axis. All right. Anything else on Rolle's theorem or the mean value theorem? I'm hoping you're comfortable with that. Along the way today, I tried to give you a little bit of extra practice and review on some of your rules for differentiation. For homework, so let's go back here. For homework, try 1 through 19, 23 through 27. 37 has a star by it. I don't know what that means. 39 through 49. Just the odds. And that's section 4.2.